In this lesson, we're going to go over exceptions to the octet rule. So we're going to start off with an example. So we know that carbon is in the fourth column of the periodic table. So it's going to have 4 valence electrons, and it's going to share those valence electrons with the atoms around it, right? And so there are essentially 2 possible exceptions to the octet rule. One is that they don't have enough valence electrons to be able to share to get a full octet, and the other is if there is a d orbital. And so let's write that down and include that here. So not enough valence to share 4 octet. So that's one way we can have an exception to the octet rule. The other one is if they have an empty d orbital. Now, for things to have an empty, for atoms to have an empty d orbital, they're going to be in the 3rd row of the periodic table. And so we're going to talk about specifically what are some exceptions. So the first exception we're going to talk about is boron. If we look at the condensed periodic table, boron has essentially 3 valence electrons, 1, 2, 3, and it needs 5 to achieve the octet, right? And so we're going to write boron here. And so we'll draw the atom and 3 valence electrons. Now, if I have 3 valence electrons, I can only share those 3 with other atoms. And so if I, for instance, share it with hydrogens, hydrogen will get its duet. But now boron has only 6 electrons around it, right? So a neutral boron is going to have 6 electrons around it. So it's not achieving the octet, and so it's violating the octet rule. And so boron, though, can also take or have an additional electron. We can add an additional electron to boron, just like we've added electrons to other atoms in the past. And now we have BH4. If we do the formal charges on these, and so formal charge equals the number of valence electrons, so boron has 3, minus the number of bonds and the unshared electrons, plus the unshared electrons. And so that would be 4 bonds, and we have 0 unshared electrons. So 4 plus 0, this would be -1. So boron here would have -1. It does have its octet, so a negative boron will have its octet, so it's not violating the octet rule, but it will be negative. We spoke earlier in the video, in a different lesson, about the tension between wanting a neutral atom and then also trying to achieve the octet. In this case, we can't have both, right? We have to have either a neutral boron with 6 electrons or a negative boron achieving that octet. So that's boron. So let's talk about another atom that violates the octet rule, but this time for a different reason, and that is going to be sulfur. If we look at sulfur on the condensed periodic table, it has 6 valence electrons. And so we're going to go ahead and draw 6 around sulfur. And so if I put 2 hydrogens there, I have a neutral sulfur, right? And then I have 8 electrons around it. Right? So this is happy because we're neutral and we've achieved our octet. Now, sulfur, because it is in the 3rd row of the periodic table, it has an empty, so we're going to say, 3rd row equals empty d orbital. And so if we have an empty d orbital, we can start filling that d orbital. So if we take a look at sulfur in a different configuration, it can have 8 electrons or it can have 10 electrons. And so I'm going to do 5 valence electrons around it. And actually we'll do 6 since sulfur has 6, but this time we'll add 8's. Now let's count our electrons. So I have 2, 4, 6, 8, 10. So I have a neutral sulfur, but this time I have 10 electrons. Now again, the reason it can do that is because it has an empty d orbital. Now I'm going to do the same thing here. I'm going to put the 6 valence electrons around sulfur, but this time I'm going to go ahead and add an oxygen and you've seen this molecule several times before, H2SO4, and this has 12 electrons. And it's also neutral, right? And so the reason that is, again, is because we're starting with sulfur, which has empty d orbitals, and so it can accommodate more electrons. Now, the third exception to the octet rule is going to be phosphorus. And so phosphorus can have 8 electrons or 10 electrons. Here, if we go back, sulfur can have 8, 10, or 12 electrons. And then boron can have 6 electrons or 8 electrons. And so for phosphorus, it has 5 valence electrons. And so it will share with 3 hydrogen, which will each have a duet. And what we'll get is a phosphorus that has 8 electrons and it's neutral. Okay, and then we have another example of phosphorus that now can actually do 10 electrons. So it is going to be neutral, and it's going to have 10 electrons. So all of these are violations to the, not all of them, but most of these are violations to the octet rule. So this has 10 electrons, and it can do that because, again, it has an empty d orbital. Sulfur is the same thing. It can violate the octet rule in 2 ways. It can have 10 electrons around it or 12 electrons. And again, that's because it has an empty d orbital. And then boron, we said, can violate that octet rule because it actually comes up short and has 6 electrons around it. And that's okay. So that's a violation of the octet. Now, the boron with 4 hydrogens around it achieves the octet, but is negatively charged. So it doesn't violate the octet rule, but it is negatively charged as it does so. And so let's go ahead and have a few examples and see. Let's talk about aluminum. So aluminum operates much like boron. So if we go back to our periodic table, the condensed version, aluminum is right under boron, so it's going to have 3 valence electrons. So if we draw that and then we share it with those hydrogens, there is our structure. And so it has 6 valence electrons. Violates the octet rule, but that's okay because it only had 3 valence electrons to begin with. Now, if I do, the next example is ALH4 minus, we can add that minus charge, which represents an extra electron, to the aluminum, and now we can have 4 hydrogens around it. Right, and if we do the formal charge calculation, it's going to be 3 valence electrons minus 4 plus 0 for negative 1. And so aluminum is going to have a negative charge, which was already indicated up here. And so aluminum is another example that violates the octet rule. Let's do one more example. It's going to be HPO3. We know that phosphorus has 5 valence electrons because it's in the 5th column of the periodic table. And so I'm going to go ahead and place my oxygens here. And I'm going to place another oxygen here. And I'll put that H right there on that oxygen. And now I'm going to go ahead and add another oxygen. The only issue is I have 7 electrons on the oxygen and 2, 4, 6, 8, 9 on the phosphorus. I want to at least achieve 10 because essentially we want either 10 or 12 on phosphorus. 8 or 10 on phosphorus. And so what I'll do is I'll go ahead and bring that electron over and that electron over. And so my final molecule will look like this. And we can go back through and see if everybody is happy. Phosphorus has 2, 4, 6, 8, 10. 10 electrons. We know that's okay because it has an empty d orbital, so it can have either 8 or 10. And then oxygen has it's 8 in this case, 8 here, and 8 up here as well. And so oxygens are happy and the hydrogen has its duet, and so this would be the structure of HPO3. And so again, this is another example of the violation of the octet rule. So to recap, you can violate the octet rule in 2 ways. Either you have too few valence electrons, like in the case of boron and aluminum, which only have 3 valence electrons, and so when they share, they're only going to get 6 electrons total, or you can have an empty d orbital, like in the case of sulfur, in the case of phosphorus, and those will violate the octet rule by having too many electrons, either 8 and 10 or 8, 10, and 12.